Okay, so good morning everyone. We're going to start with today's lecture. So in this lecture we are going to discuss a theorem which is convolution theorem. So it is a part of the chapter Laplace transform which we are already doing. Just a minute. I'll be taking your doubts later on. Let me first start with the lecture. In the last 5 minutes, I'll take your doubts. Yes, am I audible now? Is it better? Okay, so we are going to define convolution theorem. So let me first give you the statement of this and then I will make the connection of that with Laplace transform. Let fx and gx be defined for all x greater than equals to 0, then convolution of fx and gx denoted by f star g is defined as, so basically this fx and gx are two functions, both are functions of x. We are going to define some operation between them. So it is denoted by star. Remember, it is not the multiplication, it is another operation known as convolution. So f star g, that is a convolution of f and g, is also going to be a function of x. And how we are going to evaluate this one? So this is actually a integral 0 to x f of t g of x minus t dt. Obviously x greater than equals to 0. So you can say that's an assumption of a convolution, that we are working on the domains where x is greater than equals to 0. We are not working for the negative domains. So this is an integral basically. So the convolution of f and g is nothing but an integral where f and g are multiplied, but you see the multiplication, it's f of t into g of x minus t dt. So the variable which we have supposed here is t, and these will be the limits of t which will be substituted. And since here also it is an x involved, so x will be just treated as x because you have to integrate with respect to t. And finally limits will be substituted for 0 and x as a lower and upper limit respectively, and whatever you will be getting is a function of x. That is why I said this convolution is a function of x, and this is also known as convolution integral. Right, so it's ft into gx minus t dt. So this is known as convolution integral. So there are few properties. I'll be coming to the example of this, and I'll be motivating that why we have defined this convolution. I'll connect this with the Laplace transform, but right now you just treat it as a formula. Given two functions, you are supposed to compute their convolution. So this is f star g given by this. So now there are some properties associated with this convolution. We may not be proving all of them, but they are very easy to verify just by using the definition. So property number one is f star g is g star f. I'm writing it like f star g, but it's understood it is f star g of x. This is a function of x, both of our functions of x. So it's very easy to verify. What you can see here is, if I define g star f, so the g star f is going to be gt f of x minus t dt. So because you see what is the difference between f and g, what is the difference in their roles here is that f is a function of t, g is a function of x minus t, means whatever g is a function of x, but we replace the underlying variable with x minus t. So if it is g star f, this is going to be gt into fx minus t. So if you compute this integral, or you compute this integral, they both are going to give you the same final answer. So you can test it through examples. You can also prove it theoretically. So what you can do is here, you can try the proof yourself. If you put x minus t is another variable, say u, and then try to write in terms of u. You change the variable t to u. X will remain as x, but you try to change the variable to u. You will be easily able to see that how this is working. So this I'm leaving to you. You can try. Otherwise, as such, we are not going to prove it. And now I'm going to list the next properties. So the first property is known as commutativity, that the convolution functions are commuting in the convolution operation. F star g is same as g star f. The second property is associativity. F star g star h is f star g star h. That is, you can take convolution of three functions also, and this does not matter whichever order you take it. That first you find f star g, convolution of f and g, and then whatever is the answer turns out to be, then you take its convolution with h. And other right hand side is telling you that first you take convolution of g and h, and then you take its convolution with f, so the answer is going to be same. And then we have few more properties. We are as such directly not going to use them, because we will be doing most of the numerical questions. These are mostly used in proving certain other theorems, or you can say doing theoretical kind of questions. So we will see if we have to use them somewhere, but right now I'm just listing them, and you want to verify them that how they are true. So this will be very easily done if you just apply the definition of the convolution. Right, so now let me give you some questions after these properties, so you verify yourself. It's basic integral, you can do that. So now let me give you the examples, that how to find convolution of two functions. So this is the question: find f star g where fx is x, gx is e raised to power minus x. So suppose you are given two functions and you need to find their convolution. So let's see how we are going to do this one. Okay, so we're just going to use the formula. So f star gx is going to be the integral 0 to x ft g x minus t dt. So let me now put the value of f and g here. Just a minute. Let me put the value of ft here. What will be ft? It will be t, because okay, it's a function of x, but here we are treating it as a function of t. So it's just whatever is fx, you just replace x with t. So this is t. Now what is gx minus t? So this is gx. Gx minus t is going to be e raised to power minus x minus t. So you just replace x with x minus t. So this is e raised to power minus x into e raised to power plus t. So that value I can substitute here, right? So now it's easy to see that I can write this e raised to power minus x outside the sign of integral, because I am integrating with respect to t variable. So whatever will be the function of x here, if something can be taken outside, you need to take it outside, because when we are solving this integral, you do not treat x as a variable now. Your variable is t. X is going to be simply substituted in the end in the form of a limit. So if any term is coming inside the integral which is purely a function of x, and you can take it outside. So e raised to power minus x I took outside. So this is t e raised to power t dt. It's very easy to solve this integral, right? So very quickly. So first function integral of second, the limits, minus integral derivative of first function, which is 1 e raised to power d dt. So by parts I did the integration. So now you substitute upper and lower limit. So this will be x e raised to power x minus 0, because for t you have to put 0. And this one is the integral is e raised to power t. So it's e raised to power x plus 1, because the lower limit will be e raised to power 0 and there is a negative sign, so it will plus 1. So this is the answer, x minus 1 plus e raised to power minus x. So this is what we were looking for, convolution of two functions where it is this. So these kind of questions are very easy to do, that you are given directly the functions and you are supposed to find a convolution of it. So just you need to solve the integration, and whatever will be the answer, that is your final answer. So now I will be connecting. So you can do plenty of these kind of examples. You will see, you just need to remember the formula and solve the integral. So for this particular kind, I will not take the more examples. Now I will make a connection of this with the chapter which we are into. So we are doing Laplace transform. So let me connect the convolution, the concept of convolution with Laplace transform. So for that, we have a theorem which is known as convolution theorem. So I'm going to go a little down here, right? Convolution theorem. So this theorem is going to connect the two things. So let me give you the statement. Let fx, gx be two functions that are piecewise continuous and of exponential order C. I'm still to introduce these two terms. This part I have left for the end of the chapter. When we will be finishing the chapter, then I will be explaining you the meaning of these terms, piecewise continuous and exponential order, right? Right now we are just assuming that they are there and using them for the statements. For all x greater than equals to 0. So these are the actually two conditions for Laplace transform existence, that if fx and gx are two functions whose Laplace transform is existing, then Laplace transform of f star g of x is equal to, uh, 1 second. Uh, uh, Yeah, I'm back here. So, yeah, let me complete the statement of the convolution theorem, which says L of f star gx is L of fx into gx, which is fp into gp. So we know the capital F is the Laplace. So fp, just a minute. The capital Fp is the Laplace transform of fx, and capital Gp is the Laplace transform of Gx. Let me complete the statement, then I will explain you the meaning. Because whenever any property or any theorem we are stating for Laplace transform, simultaneously we can also define it for inverse, that what is going to happen with the inverse. So from the statement, you can find that L inverse, L of f star g is fp into gp. So L inverse of fp into gp is going to be f star g, which is obviously going to be a function of x. So this is the, actually you can say, main result of convolution theorem, because this is where the application of convolution theorem is. Because the question might be occurring in our minds, why we are studying convolution theorem. It is because it is helpful in finding Laplace inverse of some functions which are otherwise difficult to find. Because in last lecture I introduced that whenever we are solving initial value problems using Laplace transform, then we know in the end we have to take inverse Laplace transform. So when we have to take inverse Laplace transform, so we have a difficult function sometimes, and we usually adopt the way of method of partial fractions, if you remember the examples we did in the previous lecture. So this will help us, this formula will help us in simplifying the things. Now, so you can see that means there is a function whose Laplace transform is equal to the product of this, which is L of fx into, let me just a minute, where is the option? Yeah, let me just skip this one. Let me write it again, the more precisely. It is just this. Yeah. It will be this way, easier to remember. So we do have a function whose Laplace transform, if you take, this is equal to the product of individual Laplace transform. So this is L of fx into L of gx. So from here, you can see that, just a minute. Okay, is the statement clear to everyone? Yes, is the statement clear to everyone? That we do have a function like this. Now I'll do example and it will be better clear. Because, because we know the property of linearity, we know that when we add two functions, let me use the square brackets. When we add two functions, fx plus gx, or subtract two functions, we know that because of the property of linearity, it is L of fx plus minus L of gx. But the same thing does not happen with the multiplication. This is not equal to L of fx into L of gx, because this is true because of the linearity property of Laplace transform, because Laplace transform is a linear transformation. But this is not true, that L of fx into gx is not equal to L of fx into L of gx. But this one, if you look at it separately, is now established. This is equal to Laplace transform of some other function, and that function is not f into g, that function is f star g, right? So this is what is this convolution theorem is telling us, that there exists a function which is the convolution function, whose Laplace transform, if you take, that happens to be the product of individual Laplace transforms. So it is expressed in this form, fp into gp. And equivalently, if you take the inverse of this side, so you will get this. So this has a major utility in solving few questions. So now I'll be giving you example. From there it will be clear to you that in what kind of questions we are going to use this one. I have already told you the utility majorly in the questions where we are solving initial value problems, but apart from that also it can be used. So let's do the example. With that you will be more clear with the result of this. So the example is, find Laplace inverse of 1 over p minus 1 raised to power 5 into p plus 2 square. This is what your question is given to you, and suppose you want to solve this one. You want to find Laplace inverse of this function, right? So suppose this happens to be the right hand side function of any initial value problem, but suppose this is a question. Otherwise, what, how will you do? Suppose you do not know convolution theorem. What do you suggest? How will you find the Laplace inverse of this function if you do not know the convolution theorem? What is the way? Yes, you have to break in partial fractions, split out the terms, because we know that way it is easy, or because it is not becoming any standard formula, right? You have the list of standard formulas. So whenever we are not getting the standard formulas, so we try to break into some other form where we can use the standard formula. So you know the power, you look at the power. It's p minus 1 raised to power 5 into p plus 2 whole square. So it's going to be quite complicated if you are going to do with this the partial fractions. So we can do it using convolution theorem. So using convolution theorem, so what you have to do is break it into two functions. You write this is equivalent to fp into gp. So this is as a product given to you. So you have to identify suitable fp and suitable gp. So what choice of fp and gp you will take? by looking at this function which is given to you. What fp you will take? 1 over p minus 1 raised to power 5, and gp is 1 over p plus 2 whole square. So it makes the obvious choice that you break the given function, because it's not every time you will be given the function in this form, that they will not tell you explicitly that this is capital F and this is capital G. You will be just given the function. It is up to you how you cleverly break it into as a product of two functions, identify them individually, because this makes sense. So we will be breaking it in a way so that we have some functions f and g whose standard Laplace inverse is known to us. So now this capital Fp is such a function, I know its Laplace inverse transform, and I also know how to compute Laplace inverse transform of this function. So this is in this form. So now you use the convolution property. So convolution theorem tells you that Laplace inverse of Fp into Gp is f star Gx, where what is f? Fx is Laplace inverse of Fp and Gx is Laplace inverse of Gp. This is how you have to use the convolution theorem. So all what you need to do is now find a convolution, which is actually solving a integral. So for that, first you need to find small f and small g. So what is small f and small g? Yes. So small f, capital F, sorry, is Laplace inverse of Fp. It is Laplace inverse of 1 over p minus 1 raised to power 5. Yes, tell me, what is this? And what is Gx? Yes. What is small f and what is small g? Yes, you can raise your hands and let me know the answer. Yes, so this one is going to be e raised to power x, x raised to power 4 by 4 factorial. Because for computing this, actually, we are using the first shifting theorem. So first shifting theorem is, okay, that this Laplace inverse is equivalent to Laplace inverse of 1 over p raised to power 5, and then because p is been replaced with p minus 1, so it needs to be multiplied with e raised to power x. And what is Laplace inverse of p raised to power 1 over p raised to power 5? This is x raised to power 4 by 4 factorial. So this is small fx, and similarly you can find small gx. So this is shifted with e raised to power minus 2x because p is changed with p plus 2, and then Laplace inverse of 1 over p square. So Laplace inverse of 1 over p square is x. So you got the two functions, small f and small g. So from this step onwards, your question is similar to the previous question, that you are given two functions, you need to find their convolution, right? So for finding convolution, we need to use the formula for convolution, which is f star gx integral 0 to x f of t g of x minus t dt. So you got fx and gx. Just you got fx and gx. What is fx? Fx was e raised to power x, so I have to write in form of t now, and gx is x into e raised to power minus 2x. So this is x has to be changed with x minus t, and e raised to power minus 2x has to be changed with x minus t dt 0 to x, right? So from this integral, what you can do is e raised to power minus 2x by 4 factorial. From this term, you will get e raised to power minus 2x, and this 4 factorial can be taken outside. E raised to power t raised to power 4, x minus t, e raised to power 2t dt. So this 2t plus t, that can also be combined, and it makes it e raised to power 3t, right? So this is the integral now you need to solve, and this further can be split it into two parts because this is x minus t. So one will be x times e raised to power minus 2x by 4 factorial 0 to x t raised to power 4 e raised to power 3t dt, and the other is going to be minus e raised to power minus 2x by 4 factorial 0 to x. So this is t is there. So t raised to power 4 on multiplication with t will be t raised to power 5 e raised to power 3t dt. So if you are able to solve these integrals, these two, so you are going to get your answer, because whatever the multiples of whatever the functions of t you will be getting, you just put upper limit and lower limit, final answer you will be getting. So from this step onwards, you do it yourself. You can discuss the answer amongst yourself. Right now I do not have the final answer because I have not solved it completely, but you can try this. It's doable, it's lengthy, but it's doable, right? So integration by parts, you have to use multiple times to get the value of this integral. So this example was purely to give you an idea that if you do the same question by method of partial fractions, it's going to be it's going to be much complex. But if you do it with this way, it's going to be though lengthy but doable. Means the calculations are not difficult, or you will not stuck at any point of time. So that was about this example in which I have shown you that how to utilize convolution theorem to find the value of certain Laplace inverses. So next application of convolution theorem is this question, which is again solve the initial value problem. Y double dash plus 4 pi is cos 2x. So you see all the things are connected because the main application of inverse transform I told you is while the solving the IVP. So now for finding inverse Laplace transform, we are saying convolution theorem is there. So ultimately convolution theorem can be used to solve the initial value problem, but obviously it will be used in the last step only, where we will be required to find the Laplace inverse of the final function. Okay, so let me just do this calculation for you. So say this is your given initial value problem. So the first steps remains the same, that you take Laplace transform on both sides. So, and then on the left hand side, you use the property of linearity. So L of y double dash is p square, L of y minus p y0 minus y dash 0, and this is 4 times Ly. And on right hand side, Laplace transform of cos 2x is p over p square plus 4. So on using the initial conditions, y at 0 is 0 and y dash 0 is 0. So these two terms are going to be 0. So I'll be just left with p square plus 4 into Ly is p over p square plus 4. So this gives me Laplace transform of y is p over p square plus 4 whole square. So we know what is the next step. The next step is now to find the inverse Laplace transform. So y is going to be inverse Laplace of p over p square plus 4 whole square. So at this step now again it's your choice. If the function happens to be very easy, that you can very easily do with the method of partial fractions, then there is no need to use convolution theorem. But if you think it is difficult to use method of partial fractions, so you try doing it with convolution theorem. Or otherwise, if it is mentioned in the statement of the question that use convolution theorem, then obviously you have to use convolution theorem. So for using convolution theorem here, I need to write it in a particular form. I need to write it as a product of two functions. So some fp into gp. Yes, what should be my choice for fp and what should be my choice for gp? because whatever is given, I told you in the previous example that it will be given to you in a form where you have to cleverly decide that how I have to break it as a product of two functions, so that I am getting two functions whose individual inverse Laplace transform is easy to find. So one choice of, you can say, fp means one function is this and the other function is this. So because in the numerator there is p, so I have split it up like this: p over p square plus 4 into 1 over p square plus 4. So this fp is p over p square plus 4, and this gp is 1 over p square plus 4. What is L inverse of fp? So this is L inverse of p over p square plus 4. So this is, we know, is cos 2x, right? This is cos 2x. And now the next one is the GP. L inverse of GP is sine 2x by 2, because we have a over p square plus a square. So a is 2 here, but that 2 is not here. So I have to write it like sine 2x by 2. So I got fx. So this is my fx and this is my gx. So once you got fx and gx, so according to convolution theorem, your Laplace inverse of Fp into Gp, which is your required answer, which is actually y you are looking for. So this is the convolution of small f and g. So you got small f and small g. All what you need to find is their convolution now, right? So convolution of f star g. Yes. So I'm writing that integral 0 to x ft g x minus t dt 0 to x. F is cos 2x. So this is cos 2t. G is sine 2x by 2. So this is sine 2x minus 2t by 2. So this integral now we need to solve. Again, not to tell you, mention again that you have to integrate with respect to t. So you treat your x as simply a variable here. So what formula you are going to use here for solving this integral? Yes, it's cos A into sin B. So the formula which we are going to use is sin A plus B. So that will make it sin 2x. This is A, this is B, minus sin A minus B. So A minus B means 2t minus 2x plus 2t, and this by 2 I have already taken outside, and one more by 2 will be coming, because 2 cos A sin B is sin A plus B minus sin A minus B. This is the formula which I am using, this one. So it's cos A sin B. So 2 will be taken to this side. So 1, 2 is here. So this is my A and this is B. So you put that into the formula and you will get to know that. So this is 1 by 4, 0 to x sine 2x dt. So I'm splitting up into further intervals, further integrals. So minus 1 by 4, 0 to x. What is this? Sine 40 minus 2x. Yeah, 2t plus 2t will be 40 minus 2x dt. Now the first integral is, I can take sine 2x outside because the integration is with respect to t. So when you integrate with respect to t, it will be x minus 0 will be the answer. And the second integral, yes, the integral of sine is minus cos. So ये plus हो जाएगा. Cos 4 से divide होगा because 4 is coming as a multiple of t, and then you have to substitute the upper and lower limit. So the first term is x by 4 sine 2x, and the next term is 1 by 16 upper limit yes, 4x minus 2x, because आपको substitute करना है, you have to substitute for the t in place of x. So cos 4x minus 2x minus cos. So in place of t you have to put 0. So it's cos of minus 2x. Yes. X by 4 sine 2x plus 1 by 16. Cos 2x minus cos minus 2x. So done. That is 0, because cos of minus 2x is same as cos of 2x. So the final answer is just x by 4 sine 2x. This is your final answer. This gets cancelled. So that is the answer. X by 4 sine 2x. So this was one big question in which I shown you that how to use convolution theorem to solve initial value problem. But obviously ultimate usage of convolution theorem is only in the final step where we have to find Laplace inverse. Yes, please ask if you have any doubts. L inverse of G, P, Raghav, you're asking. Let me just. Yes, this was GP. This was GP 1 over P square plus 4. So we know the formula of Laplace transform of sine AX. So that is A over P square plus A square. So if I take A is 2, so I have to have L of sine 2x will be 2 over P square plus 4, but this is 1 over P square plus 4. So when I take the inverse, so this has to be sine 2x by 2. So that is what I have written as the inverse, sine 2x by 2. So this is very much important. You have to take care while applying this formula in many of the questions, that because if p is in the numerator, then it is straightforward, it is cosine. But if nothing is there in the numerator, that means it will be equivalent to the sine function, but you have to take care of the constant. Had it been 2 over p square plus 4, we would have directly written sine 2x, but it is 1 over p square plus 4, so by 2 needs to be divided here. Okay, so this is what we had about the convolution theorem. There are more examples now. You can try those examples from the book itself and from the tutorial sheet. I'm going to go ahead with the next topic. So you know the utility of convolution theorem now. So the next is, we are now going to define second shifting theorem, or you can say second shifting property. We have done first shifting property and we have done other properties. They did not have any names. The properties were like multiplication by t, division by x, or multiplication by x, derivative of fx, integral of fx. So the properties were like that, but this is the having a name, second shifting property. So to define this theorem, first we need to know a special function, a function of different kind. This is known as unit step function, also known as Heaviside function. This Heaviside actually is the name of the mathematician who defined this function for the first time, used it. So let me give you the definition of this function, because when you understand this function, this will be used in understanding the second shifting theorem. So this is defined like, this function is defined by ux is the notation, and it is also in some books and some authors use the notation hx, but we will be more conveniently using ux for the unit step function. So it is a piecewise function, piecewise continuous function, which is defined like this, that its domain is all real numbers. So for all real numbers it is defined. For negative numbers the value is 0, and for positive numbers the value is 1, and exactly at 0 what is the value? That is 1. So it is clearly having a jump discontinuity. There is a discontinuity, right? jump discontinuity at x equals to 0, because if you draw this function graphically, just a minute, yeah, if you draw this function graphically, so what is going to happen clearly, that for negative x, if this is x, the value is 0, and then at x equals to 0 it takes value 1, and for all positive numbers the value is 1. So it's a step function, as you can have the visualization graphically why it is called a step function. And we draw a open hollow circle here to mark that at x equals to 0 this is the value, not this one, because equality is here. So this is 1 unit, so that is why it is called unit step function. Right now, this is having many applications in signals, and I'll give you a few more applications, then we'll be doing the particular examples. Unit impulse functions are very frequently occurring in the differential equations, which are defining the evolutions of charge or current in electrical circuits. And other than that also it has many applications, but particularly we will be using it to help us mathematically in solving the Laplace transform and Laplace inverse transform. How we will be using it, that part will be explained by second shifting theorem, but right now we just need to first understand the definition of this function. So I hope the definition is clear. So it's a piecewise continuous function having a jump discontinuity at x equals to 0. We will be using its another variation which will be more frequently used. So if you just shift the 0 somewhere else, so say u of x minus a. So u of x minus a, or the Heaviside function x minus a, 0, x less than a, 1, x greater than equals to a. So instead of having jump discontinuity at 0, there is a jump discontinuity at some other real point. So that real number can be anywhere on the line. This a itself can be negative or positive, wherever it can be, but it is like it is shifted somewhere to the point A. So graphically, what is going to happen? So suppose this is the point A, then before the point A, the value of the function is 0. At A, there is a jump. Jump is still of the same magnitude, 1 unit, and this is how this function looks like. So this is unit jump. Also known as, these functions come in the general category of impulse functions. Right, so I will stop here. Will not be able to do the second shifting theorem because it needs time to understand that. So that's all for today. You can ask me your doubts if any. Yes, Uday.
मैम ये जो मैम ये अभी जो मैम वन नोट पे लिख रहे हैं मैम, आप ये फाइल सेंड कर देंगे?
हाँ, I will do that.
थैंक यू
Yeah,
थैंक यू मैम
that's why I've started using it actually.
थैंक यू मैम
Yeah. I'll be sharing these notes. इससे previous lectures के जो notes हैं वो मेरे पास hand written हैं. इतने proper नहीं है, but whatever it is, I will upload them also. But for this one, I'll be uploading the same notes. I just need to do a little bit editing with this one. Yes, Tanmay, you're asking me to scroll up. Yes, Vidushi, what is your doubt? How to find fp and gp in the function p plus p square plus 4 by p plus 1 into p square plus 4. So you need to first write it into this form. E raised to power 4t sine 2t cos t. Let me just write that. E raised to power 4t sine 2t cos t. So that is your doubt. You want to ask me how to find Laplace transform of this. So for this one, you will be doing it in two steps. For this, first you can use the uh, sine AB formula, which we just used, cos A sine B, right? You can write it like cos A sine B. It's one and the same thing, sine A cos B, cos A sine B, howsoever you want to write, whichever A, whichever B you want to treat. For this, you can use the formula sine A plus B minus sine a minus b by 2, and then for this you find the Laplace transform. For this, Laplace transform can be easily found by just splitting into two terms, because you can use the property of linearity. For the first term you find, for the second term you find, and then multiplication with e raised to power 4t means shift, first shifting theorem. So first shifting theorem means whatever will be your answer of this, you change p to p minus 4. So that is how you have to do. So whenever exponential function is coming in a product and you need to find the Laplace transform, so you just forget the exponential function, and whatever is a remaining function, for that first you find the Laplace transform. And if that is also not straightforward, like in this question, so you have to think of some formulas or the connecting relations to solve your problem. Yeah, so I'll stop here now. I'll take rest of the doubts in the next class, and I'll share this notes with you. Thank you.